Dear professors, dear colleagues, I would like to introduce to your attention a report of our current theoretical study of electrochemical and photochemical switching of diarylethenes and diarylethane capped cyclization wires. First of all, I would like to introduce the institute in which I work. This is the International Institute for Carbon Neutral Energy Research. The International Institute for Carbon Neutral Energy Research is part of the World Premium Initiative of the Japanese government, and its target is to advance the world towards a carbon neutral society. Main target is the hydrogen production, and especially the production of green hydrogen from the artificial photosynthesis. Also, the hydrogen transportation and utilization and its usage in fuel cell and other energy sources. Another purpose of the International Institute for Carbon Neutral Energy Research is to capture, store, or utilize carbon dioxide. The International Institute for Carbon Neutral Energy Research is located in Itu campus of Kyushu University, and this here is its building, which will be completed within this year. Today I will talk mainly about photochemistry. However, photochemistry is not the only field of interest in which I work. I also work in molecular electronics, where I investigate with the help of non-equilibrium Green's function method the effect of the external electric fields of molecules captured in nanoscale junctions. So within this research, I try to design novel molecular devices like diodes, switches, and transistors. Another field is the heterogeneous catalysis, where with experimental co-workers we investigate the possibility to develop novel, very high selective syntheses for basic chemical reactions, for example, like the hydrogen peroxide synthesis on palladium and palladium gold nanoparticles. In the field of photochemistry, we mainly investigate the switching reactions of the diarylethane molecules and also the possibility to use diarylethane molecules in different devices in the molecular electronics or in the chemistry. It is recently well known that the catalytic activity of different nanoparticles have size-dependent properties, so we tried with theoretical methods to elucidate this mapping between properties, size, and shape of small nanoparticles. The outline of today's presentation is given here. First, I will make introduction to the diarylethane molecules and overview of the available experimental data. Then I will talk about the conductance switching through diarylethane molecules. I will show how frontier orbitals can control the switching reactions. Then I will talk about reversible and irreversible photoswitching on gold surfaces. And I will finish the talk with analysis of diarylethane capped Tufan wires. So the first part of today's presentation is introduction to diarylethenes and overview of the available experimental data. The study of the diarylethane molecules is a large field which was established here in Japan, and it is a bridge between the chemical societies of Japan and various European countries. It was widely investigated in many collaborative papers between Europe and Japan. Diarylethenes were initially discovered by Professor Irie at Kyushu University. He investigated and proposed, synthesized and fabricated over 100 different types of diarylethane molecules, which could switch photochemically at different wavelength irradiation, and they were showing different yield, different reversibility. So he detailedly investigated the photochemical properties of diarylethenes. Professor Feringa from Groningen University was the first who could achieve conductance switching through diarylethane molecules. This result was a very important result, which was foundation for the molecular electronics and for the possibility to create and realize and fabricate switching devices with molecular size. Electrochemical switching of diarylethenes was investigated both by Professor Brown and Professor Uchida. There are many theoretical researchers who work in the field of diarylethenes, Some examples are shown here of some leading groups around the world. This is Professor Nakamura from Mitsubishi Chemicals, Professor Jacquemin from Nantes University, Professor Yurikawa from Kyushu University, and Professor Friedrich from Leipzig University. The simplest diarylethen molecule is the stilbene molecule. It is exactly what the name says. It is an ethane molecule which is disubstituted with aryl subunits. The stilbene molecule, there is a bond rearrangement within the stilbene molecule under thermal conditions or under photoradiation, or there is also possibility for electrochemical switching as oxidation or reduction. And then as a result of this bond reorganization, the open ring form can switch to the closed ring form. The same can occur with the closed ring form, again in the ground state as a result of a thermal reaction, or as a result of photochemical excitation or electrochemical oxidation or reduction. The closed ring form can be switched to the open ring form. Now this is a very interesting reaction because if the both forms possess different electronic properties, then it will be possible to switch either thermally or photochemically or electrochemically between two distinct systems with two distinct kinds of physical properties. Now, the open ring form and the closed ring form are characterized with very different pi-electron systems. The open ring form is characterized with large dihedral angles between the aryl subunits and the ethane subunit. Because of these large dihedral angles, there is large fragmentation of the pi-electron system. Indeed, the open ring form can be considered as 1,2 diaryl-substituted ethane. The closed ring form, on the contrary, has a very planar structure and very well delocalized pi-electron system. Its pi-electron system resembles polyene molecule, and actually, for more complicated diarylethanes, it can be considered as alpha-omega disubstituted polyene. From the grounds of the physical chemistry, we know that the fragmented pi-electron system of the open ring form and the polyene-type pi-electron system of the closed ring form should possess very different physical and electronical properties. The most important difference in the electronic properties will be the ultraviolet and visible spectrum. The long conjugated pi-electron system of the closed ring form will result in light absorption within the visible part of the spectra, and these molecules will have different color. The strongly fragmented pi-electron system of the open ring form, on contrary, will result in light absorption in the UV part of the spectrum. In this way, with different wavelengths, with different irradiation, spectral irradiation, it will be possible to irradiate and switch selectively between the closed and the open ring form. Now, this is very important for the selective switching reaction. We know that well-delocalized pi-electron systems possess very good conductive properties for electron conductivity, and in this way it is expected that the closed ring form should be a good conductor. On the contrary, fragmented pi-electron systems should possess semiconductive or insulating properties, and the open ring form should be insulator. Thus, thermally or by irradiation with different wavelengths of light or electrochemically, it would be possible to switch the conductance in a nano device. Another possible application of diarylethanes is switching of magnetic properties. We know that two unpaired organic radicals would overlap and interact well through well-delocalized pi-electron system. However, through a fragmented pi-electron system, this overlap will be minimized, so high spin will be stabilized. In this way, we can achieve switching, molecular magnetism switching, between a high spin state and a low spin state. Other possible applications for diarylethanes are fine chemical synthesis, host-guest interactions, labeling of living cells, novel anti-cancer drug synthesis, and others. Cis-2-ben is a very interesting molecule. However, it undergoes several undesired reactions which can reduce the the photoswitching yield. One of the undesired reactions is dehydrogenation of the closed ring form. As a result, phenanthrene is formed and the phenanthrene is excluded from the photochemical reaction. The thermal switching between the open and the closed ring form is undesired because we would like to be able to control exactly the switching reaction by different wavelengths of light or by different oxidation reactions. That's why the thermal ring opening of the closed ring form should be avoided. Another possible undesired reaction is the cis-trans isomerization of the open ring form. If it occurs and if the trans-2-ben form is achieved, then the trans-2-ben form is spatially unfavorable for switching back to the closed ring form. Many kinds of diarylethen molecules were investigated and published by Professor Irian, and he managed to improve significantly the diarylethen molecules. Some of the best investigated candidates of diaryletens are shown in this field. By introducing, for example, the cyclopentane ring, the cis-trans isomerization of the open ring form is blocked. By introducing of the both methyl groups, also the dehydrogenation of the closed ring form is blocked, and by adding electron acceptor groups in the molecule, reduces the possibility for thermal ring opening of the closed ring form. In 2003, in the laboratory of Professor Fernando was observed for the first time photochemical switching of conductance in a mechanically controllable break junction. Diarylethen molecules were placed between two gold electrodes, and then the closed ring form was irradiated by visible light. As a result, the open ring form was formed, and a conductance reduction in 3 orders of magnitude was observed. However, this reaction had a drawback. It was impossible by irradiation with ultraviolet light to switch the open ring form back to the closed ring form. Now, these molecules easily switch in solution, but obviously once attached to the gold electrodes, their switching properties are blocked. 3 years later, as a result of experimental design, the spacer between the diarylethen unit and the gold electrode was changed, and a reversible switching between the open ring form and the closed ring form was achieved. Now, it is very interesting from theoretical point of view to understand the reason for the reversible and the irreversible switching in the environment of the gold electrodes. In 2005, Professor Brownie managed for the first time to observe electrochemical switching of diaryletens. In an oxidation reaction of the open ring form, he achieved the closed ring form dication, and then in a consequential reduction, the closed ring form was insulated. The electrochemical and the photochemical switching are addressed as two different distinct processes, two different kinds of switching of diaryletens, and also it is interesting to explain them by the means of the theoretical science. Diaryletens were also investigated as part of complex organic molecules. The aim was to combine conductive wires with switchable units. The result of such experiment would lead to long switchable polymeric chains, which can be used in electronics or different electron transport devices. So the diaryleten molecule was combined with thiophan wires, and it was shown that the open ring form could switch photochemically to the closed ring form. The closed ring form could switch photochemically to the open ring form. However, the electrochemical switching of the open ring form was lost, and instead of it, electrochemical switching of the closed ring form was observed. First, I will introduce our results about conductance switching to diaryleten molecules. The conductance switching was investigated with the non-equilibrium green function method. The details of the non-equilibrium green function method are shown in this slide. For our simulations, the diarylethen molecules are placed in the nanogap between two gold electrodes. The formalism of the non-equilibrium green function method is shown below. We have the infinite Hamiltonians of the both electrodes and the finite Hamiltonian of the molecule. We also have the overlap Hamiltonians, the overlap interaction matrices between the molecule and the both electrodes. Now the conductance can be given as a function of the transmission probability, which is the probability of an electron to pass from one electrode to the other electrode. The transmission probability can be calculated from the Green's function of the system. A major problem in the non-equilibrium Green function method is the different dimension of the Hamiltonians of the electrodes, which are infinite, and the Hamiltonian of the central region, which is finite. Several linear algebra transformations lead to a finite Green's function, and then we can easily find the transmission probability. It is important to know that these gamma, they are called broadening functions, and they depend mainly on the electrodes and on the coupling of the electrodes with the molecule, are very important for the conductance. If one of them equals 0 or has very low value, then no electron transport is observed. This is important for the further discussion in this presentation. Now we've performed the simulation with the non-equilibrium green functions method combined with density functional theory, and indeed we got very good agreement with the experiment, and we've calculated two orders of magnitude conductance difference between the closed ring form and the open ring form. Below are shown the transmission spectra, and we can see that the conductance is mainly achieved through the highest occupied molecular orbitals of the systems. In the closed ring form case, there is large transmission probability through the highest occupied molecular orbitals, while in the open ring case, we have low transmission probability which disappears when the bias is applied. Now we want to understand this, and here are shown the molecular projected self-consistent Hamiltonian states, which the first approximation are the molecular orbitals within the junction environment. For the zero bias case, we have good delocalization both for the orbitals of the closed ring form and the open ring form. However, as we increase the bias, the closed ring form orbitals are slightly affected. The open ring form orbitals are strongly localized next to one of the electrodes. We try to understand the reason, and we believe that the reason for that is the effect of the external electric field. Now the open ring form orbitals can be considered as a linear combination, slightly overlapping, of two slightly overlapping orbitals which are localized on the both real parts of the molecule. When no bias is applied, when there is no external electric field, this linear combination results in phase and out of phase linear combination. However, when the external electric field is applied, it will stabilize one of these localized orbitals, and as a result, we will observe a localized case. So the reason for the conductance switching between the open and the closed ring form is in its molecular orbitals and in the interaction of the external electric field with the molecular orbitals. Second, I will talk about how the frontier orbitals control the switching reaction. Here are shown some of the computational details. The calculations are performed with the TurboMol program. The ground state calculations are performed with density functional theory and D3-LIP hybrid functional. The excited state calculations are performed with time-dependent density functional theory and again D3-LIP functional. Energy and spectral calculation are calculated with triple zeta valence polarized basis sets, which should yield in very good accuracy. One-dimensional and two-dimensional potential energy surfaces are calculated with density functional theory for ground state and time-dependent density functional theory for excited states. When the excited states are calculated, only vertical excitations were taken into account. In the one-dimensional potential energy surface, the reaction coordinate is the two ring-closing carbon atoms. It is varied between 1.3 and 4 angstroms. In the two-dimensional potential energy surface case, there are two possible reaction coordinates. It is the distance between the ring closing carbon atoms, and also the dihedral angle between the ethane part of the molecule and the aryl part of the molecule. First, here is shown the geometry of the open ring form. In the open ring form, the distance between the two ring closing carbon atoms is about 3.6 angstrom, and the structure is characterized with large dihedral angles of about 50 degrees. The bond lengths are just like it was expected from the pi-electron system. There is a short bond length, which is the bond of the ethane subunit, and long bond between the ethane and the and the both aryl subunits. In this slide are shown the frontier orbitals of the open ring form. Now, in order to understand the switching reaction, we have to analyze well both the four frontier orbitals, HOMO -1, HOMO, LUMO, and LUMO +1. In the case of the HOMO orbital, we have antibonding out-of-phase interaction between the orbitals, amplitudes and phases on the two ring-closing carbon atoms. This means that when we try to squeeze the molecule to close the ring, there will be repulsive interaction and energy maximization along the reaction coordinate. So the HOMO orbital prevents the molecule from spontaneous ring closing. On the contrary, in the LUMO orbital, we have bonding interaction, in-phase interaction, between the two ring-closing carbon atoms. So if electrons are taken from the HOMO orbital and put on the LUMO orbital, for example by photoexcitation, then the system will lead to spontaneous ring closing. The LUMO +1 orbital is similar to the HOMO orbital in respect that there is antibonding out-of-phase interaction between the two ring-closing carbon atoms. So if electrons are excited from the HOMO orbital to the LUMO +1 orbital, this excitation will not lead to ring-closing reaction. The HOMO -1 orbital is very similar to the LUMO orbital. It has bonding interaction on the ring-closing carbon atoms. So if there is oxidation of the molecule and two electrons are removed from the HOMO orbital, then the HOMO -1 orbital will determine the properties of the system and will lead to spontaneous ring closing. And again, here are shown schematically the pictures of the four orbitals. The HOMO orbital is a Bedford switching orbital with out-of-phase amplitudes on the two ring-closing carbon atoms. The LUMO orbital is a Goodford switching orbital with in-phase amplitudes on the two ring-closing carbon atoms. The LUMO +1 orbital is Bedford switching orbital with out-of-phase signs on the two ring-closing carbon atoms, and HOMO -1 is Goodford switching orbital with in-phase configuration on the ring-closing carbon atoms. In the next slide are shown the calculated potential energy surfaces for the ground state, first excited state, second excited state, and dication. As expected from the orbital analysis, the ground state is characterized with large energy barrier. So along the reaction coordinate from the open ring form to the closed ring form, we have energy which is increasing. The first excited state, just like it was expected from the orbital analysis, is characterized with energy minimization along the reaction coordinate. There is a small activation barrier between the open ring form and the closed ring form. The second excited state, it is a result of excitation to the Bedford switching orbital, is characterized with large energy barrier, activation barrier, similar to the ground state. In the dication state, we have energy minimization along the whole reaction coordinate, which will lead to spontaneous ring closing of the molecule. So in this way, the potential energy surfaces support very well the orbital analysis, which explains well, analytically, the switching of diarylethenes, its ring closing reaction. In this slide is shown the geometry of the closed ring form. Just like it was expected from the analysis of the orbitals, it is characterized with polyene type of geometry, which is alternating between short and long bonds. The molecule is characterized with very small digital angles. In order to understand the switching of the open ring form, of the closed ring form to the open ring form, we have to analyze again the frontier orbitals. The HOMO orbital will tend to keep the molecule planar and will not allow any large dihedral angles, which eventually will lead to ring opening. However, within the LUMO orbital, we have out-of-phase antibonding interaction between the ethane fragment and the aryl fragments. This out-of-phase interaction will tend to increase the dihedral angle to 90 degrees, which will minimize the repulsive energy between the both fragments. Now, this will be the driving force for the ring opening, because if these dihedral angles are increased, they will lead to larger distance between the both ring-closing carbon atoms. The LUMO plus 1 and HOMO minus 1 orbitals are respectively similar to the HOMO orbital and the LUMO orbital. However, they have very small amplitudes on the aryl parts, so they will not be significant for the ring opening and ring closing reactions. Again, here we have the schematic presentation of the frontier orbitals. The HOMO orbital is a bad for switching orbital, which tends to prevent the planar structure of the molecule. The LUMO orbital is a good for switching orbital, which tends to increase the dihedral angles and break the bond of the ring. We have analyzed the two-dimensional potential energy surfaces with two reaction coordinates. One of it is the ring-closing carbon atoms, and the other is the dihedral angle for geometries which are close to the closed ring form. The idea is to understand the precise mechanism of the ring opening reaction. So we can see that on the first excited state we have significant energy barrier on the direct ring opening reaction. So this is the distance between the both carbon atoms. However, there is no activation barrier along the increasing of the dihedral angle. Thus, once excited, the molecule will easily lead to increased dihedral angles, and they will lead to ring opening reaction. Then there will be a conical intersection for the larger dihedral angles, and it will lead to geometries close to the open ring form. These calculations were also supported by the geometry of the excited state. In the geometry of the excited state, we can see, which is a result of excitation, one electron excitation from the HOMO orbital to the LUMO orbital, we can see that the bond length between the two ring-closing carbon atoms is nearly the same. However, the dihedral angle was increased more than 2 times. Our results, theoretical results, were compared with the experimental UV and visible spectra. From the calculated and the measured UV visible spectra, we can see that there is a good agreement between the theory and the experiment. Next, I will talk about the reversible and irreversible photo-switching of diarylethenes on gold surfaces. The models which we investigate are quite simple. We have the diarylethane molecules, and we have only one gold atom added on each part of the molecule. Now, this model might be simple, but it turned to be sufficient to understand the switching reaction of diarylethenes in the region of the gold electrodes. Later, similar theoretical studies were performed for larger gold clusters attached to the diarylethane molecules, and the results show no qualitative difference. Here is shown the UV visible spectra and also the orbital analysis of the diarylethane molecule closed ring form with 2 gold atoms attached to it. Now, the orbitals 147 and 146 have their amplitudes mainly on the sulfur gold bond. These orbitals are very important for the conductance to the diarylethane molecule. However, these orbitals are not so important for the photoswitching, and we will not further discuss any excitations to these orbitals. Within the irradiated wavelength, this is the visible light, we have electron excitation from the HOMO orbital, which is a bad for switching orbital, to the LUMO-like orbital, which is a good for switching orbital. This will lead, apparently, to ring opening reaction. In the case of the open ring form, again we have added two gold atoms, and again we will not discuss the orbitals which are mainly localized on the bond between the gold and the sulfur. For the open ring form, the irradiation is performed within the UV part of the spectrum, and within the UV part of the spectrum we have low probability excitation from the HOMO orbital, bad for switching orbital, to the LUMO orbital, the good for switching orbital. Our computation, however, shows that the big peak within the UV part of the spectrum, the high probability electron transfer, is actually from HOMO -1 orbital, which is a good for switching orbital, to the LUMO +1 orbital, which is bad for switching orbital. As the probability of this electron transfer is much higher, the experimentalist will mainly observe such excitation, which will not lead to photoswitching reaction, and this will lead to the irreversible switching of diarylethenes. Now, in the case of the reversible switching, we analyzed again the frontier orbitals of the closed ring form. For the closed ring form within the visible part of the spectra, there is a high probability electron excitation from the HOMO orbital to a LUMO-like orbital. This will lead to ring opening reaction. In the case of the open ring form within the UV part of the spectra, we have high probability excitation, and this is the only high probability excitation, from the HOMO orbital, a bad for switching orbital, to a LUMO-like orbital, which is a good for switching orbital. Within the UV part of the spectra, there are no other high probability electron transfers which will lead to electron excitation to the LUMO +1 orbital. Thus, by changing the spacer, we could modify the UV visible spectra, and we could modify the electron excitation probabilities to the LUMO or the LUMO +1 orbital. And this is what controlled the reversible and the irreversible photoswitching of diarylethenes. Finally, I will talk about the diarylethane capped cyclization wire. Again, I would like to remind you the experimental data. In the experiment, we have the open ring form, which after irradiation with ultraviolet light will switch to the closed ring form. And we have the closed ring form, which after irradiation with visible light will switch to the open ring form. There is no electrochemical switching from the open ring form. However, there is an electrochemical switching from the closed ring form to the open ring form. First, I would like to show you the experimental UV visible spectra, which were measured by Professor Brownie. We can see here that both molecules have peaks within the visible part of the spectrum. The reason for this is that in the case of the open ring form, we still have the well-conjugated thiophene wire, and this lone pi electron system will give electron excitation within the visible part of the spectrum. However, the switching is not observed when the open ring form is irradiated with visible light, but when it is irradiated with ultraviolet light. Now, this is the analysis of the open ring form. Here is shown the structure, its computed UV visible spectra, and its frontier orbitals. We can see that the HOMO orbital and the LUMO orbital are mainly localized on the thiophene part of the wire. So any excitation from HOMO to LUMO will not lead to any photoswitching reaction. The longest wavelength excitation within the spectrum is exactly such excitation from the HOMO to LUMO orbital. This was the peak which the experimentalist observed within the visible part of the spectrum. And this is the peak which will not lead to a photoswitching reaction, and we can understand this very well from the frontier orbitals. The LUMO +1 orbital is mainly localized on the diarylethane part of the molecule, and it is a good for switching orbital, an orbital with the same signs of the orbital coefficients pointing each other and the ring closing carbon atoms. Now we could calculate that within the UV part of the spectrum, there are plenty of electron excitations to this orbital, which might lead to a photoswitching reaction. The HOMO-1 orbital is localized mainly on the paraffin part of the wire. So such orbital will not lead to photoswitching, it will be neutral for the photoswitching. And when we remove the electrons from the HOMO orbital, and the HOMO-1 orbital becomes dominating, it will still not lead to a electrochemical switching reaction. Here are shown the results for the closed ring form. In the closed ring form, we have HOMO and LUMO orbital, which are well delocalized to the whole molecule. So we have these orbitals both on the tailfan part of the molecule, and we have them on the diarylethane parts of the molecule. The HOMO orbital is a bad for switching orbital, so it will tend to keep the molecule planar. The LUMO orbital is a good for switching orbital, so it will tend to lead to ring opening reaction. And any excitation from HOMO to LUMO will lead to the ring opening reaction. So the excitation from HOMO to LUMO from the computed UV visible spectra is a high probability excitation. The LUMO+1 orbital is also similar to the LUMO orbital, and it is also characterized with antibonding interaction between the ethane part of the molecule and the aryl parts of the molecule. So it is a good for switching orbital. Excitation to this orbital, which are also computed to be within the visible part of the spectrum, will not lead to any photoswitching process. Will lead to photoswitching reaction. I'm sorry. Now, the only part we have to explain is the electrochemical switching. However, the frontier orbital theory fails to explain this. We have the HOMO-1 orbital, which is a bad for switching orbital. It will tend to keep the molecule planar and will not lead to ring opening. Now, if our orbital model cannot explain the electrochemical switching reaction, it will be apparently bad for the overall accepting of the theoretical model. So we've performed many theoretical and combined theoretical and experimental collaborations to understand the electrochemical switching of the diarylethane sexyl-fan wires. Our calculations have shown that the dication ground state is actually a diradical ground state. The triplet ground state is more stable than the closed shell singlet ground state. Now, experimentally, we know that it is very difficult to achieve such long, well-delocalized organic oligomers to have diradical form. And it is not very likely, and it is not very accepted that this structure will be stable and will exist. However, we analyzed the frontier orbitals, if it's true and if it's possible. In an open shell system, the electrons are removed from the beta orbitals, beta space orbitals. Now we can see that both beta space orbitals from which the electrons are removed are indeed the bad for switching orbitals. So there are less bad for switching orbitals in the system. And below them, we've seen that the two orbitals which compensate the orbitals from which the electrons are removed. One of them is actually indeed a good for switching orbital. So if the closed ring form was indeed a diradical dication, then our orbital model could explain the electrochemical switching. We have performed combined theoretical and experimental study, and our experimental collaborators, Professor Brownie, have measured the EPR spectra of the dication molecule. Indeed, he could see peaks in the EPR spectra, which could verify and justify that we have achieved a dication diradical form. So in this case, the theory led the experiment, and the theory discovered this very interesting diradical, which can further find application in molecular magnetism or different spintronics processes. Now, here I would like to summarize my talk, and I hope that I convinced you that the open ring and the closed ring form isomers possess different types of pi-electron systems. And these different types of pi-electron systems are actually responsible for the different electronic properties, different conductance, and different UV visible spectra. And the irreversible switching is observed due to electron excitation to diarylethane orbitals with unfavorable spatial distribution but not by quenching by the gold electrodes. And also that the occupation of orbitals with favorable spectral distribution is what actually leads to switching reactions. And most important, that the photochemical and the electrochemical switching are not two distinct, separated processes, but they both are just the same process, which depends solely on the occupation of the frontal orbitals. I would like to express my gratitude to Professor Kazunari Yoshizawa, Dr. Lee at Kyushu University, and Mr. Tsuji at Kyushu University, and also to my European collaborators, Professor Brownie from Groningen University, Professor Dix from Leipzig University, and Dr. Nozaki from Technical University Dresden. And thank you very much for your attention.